The next reaction we're going to look at is a very common reaction. It's called the Fischer Esterification, and it is the conversion of carboxylic acids to esters. We're going to find that this is a reversible mechanism, and it falls under that type 2A category. Let's start by looking at just a basic reaction. I'll just use this carboxylic acid, and we're going to react it with an alcohol. I'll draw that in another color. Let's just use ethanol. The reaction is acid catalyzed. And for predicting the products, basically what's happening here, the H from the alcohol combines with the OH from the carboxylic acid to give you water. And then the oxygen of the alcohol bonds to the carbonyl carbon. So here's the product. So we have that O-ethyl group now attached to the carbonyl plus water. So before we get to the mechanism, just a few key points to discuss with this. The first, for the acid, it's going to be a strong acid and a non-nucleophilic acid. And the catalytic quantity, because it is just a catalyst. So the most common non-nucleophilic acid, that's just going to be sulfuric acid, because that gives us the proton, but HSO4 minus, that is non-nucleophilic. Compared to like HCl, where H plus comes off of HCl, but the Cl minus can act as a nucleophile. The second feature, which we talked about when we started, the reaction is an equilibrium process. Or in other words, it's reversible. And with these type of equilibrium reactions, we have to have a way to drive this reaction to the desired products. So we want to drive the reaction to the right. And there's a couple of ways to do this. One way is to add an excess of one reagent. And basically, what that would mean is, for example, maybe you would use 1 mole of carboxylic acid, 10 moles of alcohol. And what that does is having an excess of one reagent puts a stress on the equilibrium, pushing it toward the right, and what you would essentially end up with is about 1 mole of product. So you have a large excess of one thing, and you're going to have to remove the 9 moles that are left over, but effectively you're able to convert an equivalent of starting material to an equivalent of product that way. The other way you can do this is something we've talked about before, is use a method that removes water as it's formed. So that creates a disturbance on the right side of the equilibrium, but if you're constantly pulling away water, that's going to push the equilibrium to generate more water, and that'll occur and occur until your starting materials are converted to product. So let's look at the reaction mechanism for the Fischer esterification. And again, it's going to follow that type 2A that we discussed previously. And just to keep things a little bit simpler, instead of drawing out like a complex carboxylic acid, I'll just abbreviate it with an R group. And we're going to have that, and I'm going to use methanol as the alcohol when we get to that stage. So we have acid around. Right? Take to the bank. If you have a carbonyl and acid, always your first step, use a lone pair on the carbonyl oxygen and protonate it. So that is, as we talked about before, an activated carbonyl. Meaning it's extra reactive. So now when it comes in close contact to an alcohol, like methanol, which really isn't very reactive, but the reactive component is the activated carbonyl, so those two things can react. And the lone pair on the methanol oxygen attacks the activated carbonyl carbon, and we'll push those electrons up to the positive charge. Okay, now here, what we want to do is transfer the proton from the alcohol oxygen to one of the OHs. Now you can use a shortcut and just do a single step proton transfer, but I'll go ahead and draw it out as the 2 full steps. So we'll just use a B with a lone pair to come in and take that proton. Then from there, you can write just a new H plus over the arrow, or we can just use the proton that's on the B down below here. So I'll take the lone pair on the oxygen of the OH, grab that proton to protonate it. So now I have OH2 plus. Which is a good leaving group. From here, like we've done several times already, let's use the lone pair on this neighboring oxygen. We'll push that down, and that helps in displacing the water. So here's where we lose water. And we're almost finished. All we need to do now is take that proton off of the oxygen. Just use a B. And there's our products. So we've converted the carboxylic acid to the ester. As we talked about previously, the acid is just present in a catalytic amount. And what we can see is that the acid is used up here in the first step. And then by the end of the reaction, an acid is regenerated. So it's catalytic in the acid. One other thing that I'll just mention here, as we go through, we're using this B with a lone pair as a base. And I'm fine if you just use the B to be generic, but this could be anything in the solution that has a lone pair. So just to give you some ideas of some possibilities, that B, that could equal the alcohol lone pair. It could be the lone pair on the water, the lone pair on one of the carboxylic acid starting materials, or if you use sulfuric acid as your acid, it could be the HSO4 minus. So many possibilities in the solution that could act as that weak base to take the proton.